Hello everyone, thank you for joining today's webinar. My name is Chinh Nguyen. I'm Technical Application Specialist at Dolomite. So today we will talk about the synthesis of hydrogel microsphere using the Microfluidic. We are very honored to have Ms. Anna Cameron, a PhD candidate from University of Queensland, to join us as guest speaker today. She will be sharing about her group research at Shrink Group focused on high throughput production, agarose and alginate microparticle for single-cell encapsulation of bacterial populations. So for starting webinar today, I will present about the introduction of Dolomite Microfluidic System for Hydrogel Microsphere using Microfluidic. So the content of my presentation today will include introduction, and after that we talk about the Dolomite Microfluidic System and some example for hydrogel microsphere synthesis. So during my presentation, if you have any question, feel free to give your question in the question windows or the chat window. So we will have further discussion in Q&A section as the last version, the webinars. So the Dolomite is a world leader in design and manufacture of high quality of innovative microfluidic product. So Microfluidic is our core technologies, and Dolomite is part of Blacktree Group. So we are driven by productizing science, turning scientific discovery into cutting-edge commercial product. So we are selling our cutting-edge product through the three brands. Dolomite developed the most innovative and advanced product for microfluidic application, offering a range of modular system and components. And the Dolomite Bio provides solution for high throughput single-cell sequencing and particle work. It provides a game-changing particle generation platform, which allows you to produce nanoparticle and undivided precision, quality, consistency, and control while reducing your development time and cost. About the microfluidics, it involves a combination of fluid in channel with dimension between 1 micrometer and 1 millimeters. So compare with traditional methods or the other methods. So microfluidic methods offers benefits such as, for example, it providing efficient mixing and mass transfer, and also it provides rapid heat transfer due to high contact surface areas, and it also provides consistent fluid interaction and continuous flow processing materials. So using microfluidic, it can be combined immiscible fluids such as oil and water, which enable to form droplets, or it can combine miscible fluids such as like ethanol and water, which enables to combine reagent to carry out chemical reaction, or it can change insolubility that results in particle formulation, for example, like liposome or PLJ nanoparticles. The basic concept of microfluidics we can see in the graphs or figures on this slide. So basically, with the traditional method like batching methods, the works will obtained by input of the energy into the immiscible liquids to generate the emulsion. So it will provide very high input energies with larger volume reagent required, and also it will have a poor side distribution or with the various reaction condition, and also with high input energy, so it have challenges to scale up. So with microfluidics, the droplet are pinched up with minimal input of energy. So it will be tiny reaction volume feasible with a minimal waste using microfluidic, and it can provide excellent side distribution and with consistent process condition, sorry. And because the input energy is small, so the scalable the process is scalable by numbering up. It's easy to scale up the process using the microfluidic. For hydrogel bead production, the hydrogel are manufactured by both the method, the chemical gelation or thermosetting. For the method chemical gelation, so two reagents will be combined at the pinch off at the junction, and gelation occurs in flow or in collection vessel by means of introduction of a third component. And in this case, the payload is typically brought in one or both of the equal lines. And the second method, thermosetting. So the materials are taken about the zero point and it's pinned up at the temperature control junction. And after that, it will be collected and set through cooling process. In this process, the payloads can be brought in on a hot or cold aqueous line. So with working with hydrogel bead, so it will have typical issue. For example, it will working with the viscous material, so it will have the limited on throughputs, and also gelation process is normally take a time. And also the matching reagent, for example, emulsion stabilizing oils with aqueous component and custom design chip. Here, showing some example for the hydrogel bead production. The first example is alginate bead that commonly used for cell encapsulation, microencapsulation, protein encapsulation, and API encapsulation. The second hydrogel bead materials is agarose and gelatin, so it has been used for cell material encapsulation or protein or API encapsulation. And also the polyacrylamide beads, which has a form of major and non-porous form, for example, with oligonucleotide functionalization of bead for enhanced RNA capture and to enable passage through microfluidic channels. Also, it have heavily cross-linked form, so it is for therapeutic material, for example, like radioisotope. And next slide, I would like to introduce about the microfluidic system. So with the arm is to provide a total solution for microfluidics. So Dolomite provides products which offers microfluidics modular system that is flexible and off-the-shelf solution for the complete solution for customers. For example, we have micro droplet system, we have a double emulsion system, a nano synthesis system, liposome PL, GA nanoparticle generation system. We also providing the microfluidic parts and components that individual modular accessory, like for example, like chip or connector, or pump or sensor, temperature controls, and GRs, chemicals, surfactant. Also, we can offer a custom microfluidic solution that we can design to customer requirement. For example, we can design and fabrication of chip, connector, pump or sensor with a microfluidic instrument and other microfluidic device as well. Here is three main systems for microfluidic modular system. So the first system is a single channel system that including the particle generation system like alginate, hydrogel, or lipid or PLG nanoparticles generation system. Also, it can be used as single double emulsion system and porous media system, and for educational purpose. The second system is Microencapsulated system. It is single cell encapsulation system, and for scale system we have a tailored scale systems that is high throughput system for droplet particle generation and encapsulation. Firstly, here is how the single channel system look like. So basically, it will include the 3 pressure driven pump that can provide very smooth flow for the process. So the P pump, pressure pump P pump will be connected with the microfluidic chip by using the tubing and connector, and the microfluidic chip will be located under this microscope that integrate with high-speed camera that can allow you to visualize on a process that happen inside the microfluidic chip junction. So the system was designed very flexible, so the customer can very easy to add or remove component or modular to adapt the customer's specific application. And also, the chip can be using with the different geometry to adapt with the specific application, for example, like microparticle generation or nanoparticle generation. And the second system is Microencapsulated System. It is a complete system for high throughput encapsulation of individual cell into picoliter droplets. So the system can work with small sample of hundreds microliter or less, as it has the sample chip reservoir. We have 2 independent channels. That's one channel has a volume of hundreds microliter of sample volume. The system can use for encapsulation of the single cell or DNA or the other materials as well. And the encapsulation rate can be up to 300,000 cells per 3 million droplets in 15 minutes. And the second channel will allow to do the core encapsulation with functionalized beads and all reaction mix. And the system is ideal for profiling native pair with TCR or isolating the antibody coding sequence, encapsulating cell and in hydrogels, or encapsulating the expression library for fact sorting, for example. We also provide automation and integrate with droplet analysis through the PC software with the system. Here is showing the hardware of the microencapsulated system. Basically, the system will have 3 pressure driven pump, P pump, and it have microencapsulator module, as with including the chip reservoir and the droplet junction chip, it also have temperature control unit that enable to control your temperatures between 1 to 100 degrees C with the precisely controls option. And final component is with the microscope is integrated with the high-speed camera. We have customer visualize the process which happen inside the microfluidic chip junction. The below EPG is showing how to inject the sample using the micropipettes to sample reservoir that have 2 independent channels with each have hundreds microliter volume of each channels, and the sample reservoir chip will be direct connect with the chip junction, micro droplet chip junctions, and it will connect with the P pump and by using the tubing and the connector, linear connector. So the image is showing the picture showing the microscope images that happened under with droplet junction chip, which to generate of the small droplets or microspheres in small droplet junction chip with microencapsulated system. And here showing schematics for microencapsulated system. Basically, the system have some sample reservoir chip we connect with the droplet junction chip, and 3 pump connecting with the the Microencapsulators module. So the first pump will use for delivering a cell. So the cell will inject into the first chip sample reservoir chip junction, and will delivering to the first the input channels in in droplet chip, and the second pump will delivering will delivers the oil phase into the droplet chip, and the third pump is used for the second aqueous line that that allows the other material to be encapsulated along with the cell, or to enable a pair of reagents to mix at the chip junction to form, for example, like hydrogels. And the third system of Dolomite Microfluidic is tailored scale-up system. So the tailored system can increase the output by 3 ways. So it could be increase the flow rate through individual junction, and or it can increase number of junction working in parallel. So in the images you can see there are 7 channels that integrate into one microfluidic chip. So it can work in parallel ways. So it could be increase the throughput of the system up to 7 times compared to using single channel chip junction. And the third way is increase numbering up of chip working in parallel. So if you have a look in image and bottom of the left hand, on the left hand side, so it's showing that we can integrate and we can running up to 10 chips working in parallel together by using the tailored module clamp that's integrate together. So it's able to increase the throughput of the system up to 70 times compared to a single chip system. And next slide, I would like to talk about some example for hydrogel microsphere synthesis using our Microfluidic system. So the example 1 is the production of highly monodisperse pectin particles. This example will show the use of Dolomite larger droplet system for formation of the biocompatible highly monodisperse micron particle pectin gel. So if you have a look at the images in bottom of the left hand side, so it's showing the mechanisms, the schematic of the pectin production and cross-link mechanism using the Microfluidic chip. So it has 2 steps. So the first step, the pectin and calcium EDTA will be combined and pinch off at the chip junction to make a droplet. And after droplet formulation, so it will pass to curing the process. So in this way, the product will be put into the rich of acid environment. So it will allow the pH values less than 5, and the cross-linking will be occur during the process to generate hydrogel with. If you have a look at this image, so it's showing the real image that happened inside 270 micrometer of larger droplet junction chip to make up the pectin hydrogel. So it can generate around 100-200 micrometer of the droplet, and the product after droplet formulation will be collected at the centrifuge which contain acid environment. So The below the bottom images showing the process to separating and the disperse of the hydrogel bead after the curing process. So the first image is showing the So the first image is showing the separate layers of the hydrogel bead with the oil when contained or when storing at the centrifugation tube, and the second image is showing the oil will remove and will remain only packaging bead. So after removing, we add the fluorostop and to broken down the surfactant out to the hydrogel bead, and it relieves two layers, one for the oil phase and the one for packaging beads only. So this next picture showing we add water into the packaging bead phase to redisperse the packaging bead water, and it has to easy to remove the fluorostop phase oil phase from the mix. And finally, we can get the packaging bead with dispersed in water. So here is showing the system setup for the packaging particle generation using Microfluidics. So we have three pumps using in this one. The first pump will use for fluorosurf as a continuous phase, and the second pump will for delivering the mix of the pectin and calcium the EDTAs and introduce into the droplet phase. And the third pump will be used for washing fluids. Is for flushing or cleaning system before and after the experiment to make sure that the system keep in clean condition. So the Microfluidic chip using for experiment is the larger droplet junction chip, and the process will measure the visualize. We visualize by using microscope with high-speed camera integrated with droplet monitor software for real-time droplet size measurement. As you can see in the top of the right-hand side of the presentation. So this one showing some results that we have obtained with from our lab. So in this experiment, we present the result that obtained with the three different of the Dolomite microfluidic droplet chip. So we use 100 micrometer, 190 micrometer, and 270 micrometer droplet junction chip. So the result showing in the graph showing that the droplet size with the ratio of packaging bead at the maximum throughput is showing when we change the flow rate ratio between the continuous flow rate and droplet flow rate, so we can control the droplet size or the bead size of hydrogel. Also, with the different size of the chip used, we can obtain the different range of the droplet size as well. And this image is showing the method to measure the droplet size or hydrogel beads after curing process. So the droplet will collect on glass line and measure through the imaging software after curing. So it's showing the very consistent the results compare with inline the process using our the software as I presented previous slide. And next example, I would like to talk about the hydrogel production using the Microencapsulated system. So in this example, the agarose is attractive for encapsulation and to be generated by using the microencapsulators. It's due to easy to diffuse the nutrient in or secrete factor diffuse out, And also the cell and DNAs are stable enclosed inside the bead. Also, the agarose bead used for the cell cultures like is highly defined, reproducible 3D culture condition. For example, like epithelial ethnic cultures in zero beads or with the controlled imaging cell interaction condition. With Microencapsulated System for generating of the agarose hydrogel bead, so it enables to precise control in the microencapsulator by using the temperature control unit. So with the temperature control unit, the customer can easy to and precisely control the temperature of the chip junction, the chip with between 1 to 100 degrees C. And the below image is showing the 50 micrometer of agarose bead with form with low gelatine temperature agarose. So it's showing very monodisperse with high monodisperse of sample which we generated by the microencapsulated system. And this one showing the principle of creating a hydrogel droplet. So in this case, the oil is used as the continuous phase, and the cell suspension and the gel will be mixed or combined at the chip junction, and the droplet will be formation after past the chip junction to so the cell will be encapsulated inside of the gel hydrogel bead. And if you have a look in these images, it's showing the cell can grow for a day, week in droplets. So this image is showing the cell inside hydrogel bead from right after the droplet formulation, and it after 4 days, 10 days, and after 14 days, the result showing that the cell is healthy, grow up inside the hydrogel bead. So more detail of this experiment using microencapsulated system for hydrogel production and encapsulation will be presented by Miss Anna from University of Queensland in part 2 of presentation. So I will finish my presentation in here. Thank you for your listening, and if you have any question, feel free to write out the question in the chat box or chat window or the question window. So we will have further discussion in the Q&A section as the last one in our program. Thank you.
Great, thank you, Chin. That was a really engaging talk. Anna, if you want to take over now. As Chin said, just while Anna's loading up her slides, if you do have any questions, please put them in the chat window and we'll get to them after Anna's presentation.
Trying to upload it. It does not want to share today. Okay, let's go to me. Okay, now I can.
Great.
All right, is that visible for everyone?
Yes, we can see that.
Awesome. Let me just make it visible for myself. All right. Hi, everyone. I'm Anna. I'm almost a doctor, just from the start. In about a couple of weeks, I should be. So today I'm going to present my webinar on the research I've been doing as a research assistant during the last bit of my PhD. So it's on the synthesis of hydrogel microspheres using the Dolomite Microfluidic system. The flow of it will be as follows. Sorry, everything keeps popping up in the way. We're going to have how I synthesized agarose and alginate beads, then why I did this, hint it's for single cell encapsulation, which can lead to cell sorting, whole genome amplification, as well as some isolated cell culture. They're all options, and all of them are things I have attempted, so I will discuss it a little bit further as we go through. So we use the Microencapsulated System. Specifically, I've been using the 1-2 reagent droplet chips. I use them in the 30 micrometer etch depth, the 15 and the 50. Throughout this research, it'll mainly be referring to the 30 micrometer etch depth. I also created alginate microspheres. I won't go into too much detail because Chip did a great job explaining exactly how I do make my alginate microspheres in the system. I follow the protocol provided by Dolomite for the production of highly monodispersed alginate beads for mammalian cell culture. Obviously, I'm using them for bacterial cell culture. A few changes were made in the fact that I'm using a different microfluidic chip, but it just shows that this protocol is useful across these chips if you can, as well as I increase the acetic acid concentration in order to get a stable alginate microsphere. I will discuss what I increased it to in the following slide. I also created agarose microspheres using the same droplet chip and the same setup. I have here the system that I've stolen from the website. This is my Microencapsulated System and what I work on every day. And then we've got how I use the oil to cut my cell suspension mixed with my hydrogel in order to create these microspheres. So I had to follow 2 different protocols that Dolomite had provided with a few changes. So I used the agarose bead synthesis, which gives you pretty much all the information you need, as well as the encapsulation of cells in agarose on the Nadia Innovate and our Nadia system. Again, I'm using the Microencapsulated System, but the protocol works across them. I adapted it to the change in system, as well as I used a slightly different agarose concentration. For most of the time, it's 2% low melting point agarose. I used 3%, which diluted to about a 1.5%. It just gave me a more stable particle, and it was a little easier to work with in the long term. So we created the microspheres. Here they are. We found that we could store them for months within the oil. However, within an aqueous solution, the storage wasn't quite as long. So we kept them in oil until we needed them. I was able to produce 15, 30 and micrometer average diameter microspheres by changing that etch depth that Chia talked about. If you had the 15 micrometer etch depth, I created a 15 micrometer diameter particle, 30, 50, so on and so forth. I then stuck with the 30 micrometer diameter because we needed to do FACS for the cell sorting part of it. And the maximum nozzle size you can get is 130, which is only allowable for a 30 micrometer diameter microsphere. So we have used that throughout. So I created the particles, but I wanted to quickly discuss a few of the issues that I ran into, just in case anyone needs to troubleshoot. So first off, with my alginate particles, the protocol says 0.05% volume per volume acetic acid in the catchment container. I moved it up to 0.1, small change. It gave me a stable particle. As you can see on the left top image, that was my 0.05. 0.01 was the images beforehand. I also found that there was some autofluorescent issues. So the fluorescence transfers between particles when they are in oil, not when they are in aqueous solution. So this had to be taken into account, especially when I was trying to tag cells within particles. Some particles would give me a fluorescence even if they did not have it, so I found it was better to dye them when they were in an aqueous solution. There's also specific dyes you can use if you want to look into them. We also had particle debris and contamination at times, the bottom left image. They do degrade slightly in aqueous solution. This one here had been sitting there for about a month and a half before I imaged it, but I also think there was contamination within it. We had to filter out the contamination in our particles or any of the debris that might have occurred in the production of them. We did this 2 ways. We either spun it down, or I used a polycarbonate filter and actually washed the particles through, and then flipped my system in order to pull the particles out, and that washed everything off, and then my particles were stable enough to be able to be removed. And then lastly, we cannot freeze particles to -20 degrees Celsius. Those are agarose particles, but it happened with alginate as well. We tried to freeze it for the purpose of saving any DNA we might be in there. So don't do that, but you can save them at 4 degrees Celsius. So moving past the issues that we had, we then wanted to go into cell encapsulation. So my first attempt was just using E. coli, and we did that within the 1% agarose microspheres. And you can see that here, we have definitely heavily laden the particles with these E. coli. But it did give us some good information in the fact that about 75% of them, or 3/4, appeared somewhat stuck in the matrix and couldn't move, whereas 25% of them could move pretty freely and were very happy. So we took into account that some of them wouldn't be motile within our hydrogel when we're using agarose. We then had to ensure the cells were within them, within the microspheres. So I do that on the next slide. And we wanted to achieve single cell encapsulation for our final purposes. So for checking if the E. coli was inside our microparticles, I just used an axio imager. This microscope has a very small focal depth. So if they were on the same focal plane, which they are, we could confirm that there was encapsulation. As you can see in this image, you can also make out the morphology of the E. coli and approximate their length. This was useful in a lot of applications. So we did want to get to single cell encapsulation. So I used MATLAB. There's many different ways to do it, but it's just Poisson's probability distribution to check what concentration of cells you'll need in order to encapsulate them with a single cell only. So if you look at that small graph there, you can see that approximately 10% of them would have 1 cell per particle, and then you'd get 90% of them without. Once you start going above that 10%, you start getting 2, 3, 4 cells in your particles, which could destroy some experiments, but could be helpful to others. So when we had single cell encapsulation, firstly, what I wanted to try was cell culture. So there are issues, as you can see here, with doing so. I'm sure there's other expertise, and Chip might be able to help us, but on the left, I have E. coli culture within agarose particles, which I broke out into LB media. I had washed these particles multiple times in order to get rid of any excess E. coli and left them to grow. This was actually about 2 days worth of growth. As you can see, the E. coli has spread everywhere, and I found this multiple times that the E. coli, perhaps if they were towards the outside of the microparticle, had broken into the media and had grown there quite quickly. There is also a small part where you can see there is a culture within the microparticle. It was interesting to note that cells preferred the interface of the microsphere, and I'm going to use microsphere and microparticle interchangeably, I do apologize. The microsphere and the media, or the microsphere and the oil. On the middle, we have the E. coli and agarose microspheres and oil. We have a good example down the bottom of it being cultured in the microsphere, and then up the top, oftentimes they would cling to the outside of my microparticle and grow there. Even though we're in oil, I think maybe the media that I mixed with it had seeped out, allowing them to live for a bit longer out there. And then on the right, we do have a good example. So we haven't continued with this experiment so far, open to suggestions, because we're worried about cross-contamination. I attempted to grow 2 different cells together, and they all just ended up mixing, which would be devastating if we were to do our future experiments, but could be helpful for someone else. So then, using our single cell encapsulation, we wanted to move to amplification and looking at the DNA. In order to do that, we needed to move our emulsion into an aqueous solution. So we did this using flow stop, has shown that really well. This was necessary so that we can start adding reagents to our aqueous solution for the amplification. On the left, you have the single cell encapsulation. Hopefully you can see it. There might be a few that are more than double, versus in oil versus it in an aqueous solution on the right. So once I got the cells in there, I went to attempt a multiple displacement amplification in order to look at the E. coli DNA. I think it's missing. No, there we go. So as you can see here in the green, we have the agar in, so the microspheres with E. coli in them. There was approximately 10 per well, just going off the numbers and the dilution of the solution in the green. And you can see it amplified quite nicely. And then in the red, we have our control to go against it. There are some particles that some wells with particles in them that didn't amplify, which is to be expected. We got about a 70% success rate when we were trying to amplify the DNA. However, our main issue was if there was even a slight amount of DNA or cells that were outside of the particle, which could happen in the process, it was quite a rough process on our cells, then that could have been what was amplifying. We found that amplification within the microspheres wasn't as obvious. So again, it's something that we want to work on in the future. Once we'd done the amplification, we wanted to see if we could actually extract the DNA, and it was useful, especially when we're working with hydrogels. Again, I've showed everything with agarose. I did all the way up to the last step with alginate and found the exact same results. Once I had amplified the last sample, I took it over to my qubit to get a high molecular weight DNA reading. We got about 33.7 for a 1 in 20 dilution from my original MDA'd microparticles, which equated to about 2,200 nanograms per mil of DNA. So they definitely amplified and it was there. We then ran this through our measurement, the Agilent, I don't know how to say it, bioanalyzer, and we found a similar concentration and that there was peaks showing that we were getting DNA removed from our hydrogels, which is positive to know that we can do this in the future. And then lastly, to look at the cell sorting, which will be the overall goal of our research here. We wanted to see the potential of it using our FACS. We tested particles with and without E. coli encapsulation, again, agarose particles. We were able to quite happily gate the microparticles from the solution. It was about a 90% success rate that we could remove microparticles from solution. However, we have not gotten to the point where we could isolate a microparticle with an E. coli from an empty microparticle, which will be the overall goal. I'm also not a professional at FACS, so these have been done by our handy lab tech, not my area of expertise if someone has questions. So to summarize, we were able to produce microspheres of agarose and alginate using the exact same microfluidic and setup, very handy, just using a slight adaptation of Dolomite's protocols. We created stable and pretty homogeneous particles. Then we were able to move on to single cell encapsulation, which allows us to do many things, including culture cell population from a single cell, and then work on possible whole genome amplification, in which we see DNA extraction and sorting as a possibility. Sorry, I've got two last slides. So I would like to thank the University of Queensland and specifically the Australian Centre for Ecogenomics for funding this and being so supportive, as well as my group and supervisor, Dr. Christian Ringbaker, and a special shout out to Apurva for helping me through everything. Then, was there any questions? I'll try and bring the actual question page back up too.
Great, thank you, Anna. We do have some questions that people have populated during those talks, so thank you very much. If you do have any other questions, feel free to add them now and I'll feed them onto the presenters. But first off, Chin, there's a question, can the Microencapsulator system be used for any other application? Oh, sorry, Chin, I think you're still muted.
Okay. Yeah, thank you. Great question. Yes, my answer for the question is yes. The microencapsulated system not only used for encapsulation purpose only. It could be used for particle generation, for example, like nanoparticle or in micro-size particle. So as we mentioned that the system is were designed with a very flexible system. So it can adapt customer to do many different targets for different specific application. So with the microencapsulated system, the customer also can change the microfluidic chip geometry by just only simple way to adjusting the chip. So it can allow the customer to do with the other application as well.
Great, thank you. And then Anna, are there any different mechanical properties between the hydrogels that could affect the experiment? I know you used alginate and agarose. So.
Yeah, there are, especially things like pore size. If we're looking at an enzyme having to penetrate or a cell having to be encapsulated, alginate has a far smaller pore size. I think it's around 9 nanometers, don't quote me, whereas agarose has one that's around 100 nanometers. So it gives you a little bit more room to breathe. We found that also agarose was a bit stiffer, so the particles held up a little bit better than our alginate particles did when you put it under a little bit of force or rough handling, I guess.
Fair enough. So this one came in through Chin's talk, but it might be good to have both your inputs on it. Could you recommend the oil that you would use for cell encapsulation?
Yes, for cell encapsulation, so you should have the biocompatible. You should use the biocompatible oil like fluorinous, hydrofluorinous oil. For example, like you can use for hydrofluoric ethers like HFE 7500. So it is commercial oil that contains the fluorinous function, and it is biocompatible and commonly used for cell encapsulation.
Anna?
I've tried a few oils actually, so that's a really good question. Some of them work, but the best one I found was Dolomite's Fluoro Surf. I use that, well, I use the HFE 7500 oil, and then that's a surfactant. When it comes down to it, your surfactant is going to be your most important choice.
Okay. Thank
and
you.
yes, fluorinated for sure.
And then Chin, could you talk about the different minimum batch volumes for each of the 3 systems that you presented on?
Specifically for microencapsulated system, we have chip reservoir. So with we can the customer can inject and use the 100 microliter or less than 100 microliter for running experiments. So the minimum of sample is not defined since the micro droplet generation could be generated with very small amount, in very initial small amount of the sample. So it depending on how much the sample the customer can handle for the other further analysis, like for the microscope imaging or for counting the droplet size or particle size.
Okay, good to know. And then Anna, the amount of fluorostop, or if you use an alternative droplet breaker solution, could you talk about the volume that you added compared to the emulsion volume and if it affected the viability of your cells?
That's a really good question. I played around with this a lot. I wanted to use as little as possible. We do have fluorostop and it works quite well. So I tried, I think 3 times is a lot of what is prescribed. I use 2 times. So whatever the amount of my solution is, I add 2 times the amount of flow stop. Chin might have a better answer for that one. But yes, it does affect the viability of your cell. So if you leave your cell and microparticle solution too long with your flow stop in there, you will kill your cells, which can be handy for things like, we don't know how much it ruptures the cells, but for an MDA, you want to get into the bacteria and you want the bacteria not to be motile or moving so that you can get a good MDA on it. So sometimes I would leave it there a little longer, and I found that my MDA went quite well when I did that.
Okay, cool. Could you give an idea of the time you mean by too long?
Approximately 2 minutes, less than 2 minutes.
Okay, great, thank you. And then we have a few questions on the Dolomite Microfluidic products, Chin. So one is about the speed of the camera, so the high-speed camera. Do you know how fast it is?
Sorry, could you say again the question? I cannot.
Yeah, that's fine. Just have a question on how fast the high-speed camera is.
Well, the high-speed cameras, we have specifications along with the high-speed camera. So actually, I can't remember exactly how fast this one, but if possible, we can send you our high-speed camera specification to you through the email after the webinars. I think it's much more helpful for you.
And then also the microfluidic chips that we use, obviously we use glass chips. Do you have any benefits to add over the use of glass chips over PDMS chips and their longevity as well?
Okay. Well, so we use glass material for making in-house our microfluidic chip, so it can provide to customer to use it many times a long time. It's reusable, so it depending on how the customer handling the chip in the good condition. So it could use or they use up to 100 times or a couple of months in use. Also, using the microfluidic chip, it has good transparency, the properties, so the customer can very easy to visualize the process under microscope compared with the PDMS or the polymer chip. And also with the glass chip, so we do a very precisely etching, so it can provide very smooth channel with the precisely channel depth and channel the dimension compared with the other polymers chip. So the surface area could not be very smooth like glass chip.
Okay, great, thank you for that. Anna, we have a question of whether the agarose beads lose water slowly over time and whether this impacts the cell lifetime.
That is a great question. I was trying to think about it, actually, I saw it there. I don't think they could so much lose it in the oil. If you are surrounded by oil, the aqueous part of it can't go far. Maybe they're oversaturated and it would slightly go around the edges, like where we can see it growing. But does it kill the cells over time? If there's only a certain limited amount of nutrients in that microparticle and you've got it in oil, yes, once they eat all that nutrients up, then they will die. But if you were to break them into an aqueous solution, then you wouldn't have either of those issues.
And then one for probably both of you, if you know any other polymeric materials that could be easily used, considering the high viscosity for the microencapsulation process. So apart from agarose and alginate, if there's anything else that you know of that is frequently used.
I think Chin touched on polyacrylamide is a commonly used one, but I don't think you'd want to use it for encapsulation.
Anything else that you want to add, Chin?
Sorry, I cannot hear clearly the first sentence of the question. So could you repeat it?
Just if there are any other polymeric materials that you would use or you have seen used for microencapsulation.
Well, so yeah, so basically we use like agarose or the gelatine or alginate hydrogel for encapsulation. With the high viscosity, I have no comment on that one.
Okay, thank you.
If you wanted to use something that wasn't a polymer, you could start going to things like collagen gel and Matrigel, especially if you're looking to grow your cells in that matrix.
Mm-hmm. And then Anna, have you ever used the system for probiotic encapsulation, or if anyone else in your group has? If so, how good is the shelf life at room temperature or at 4 degrees?
I have not. However, one of my friends doing his PhD works in this area. He does not use one of these systems, and instead he had to make it more high throughput. So he went and used a spray dryer to do this for his sample, coating it in alginate and then storing it at 4 degrees. But yeah, I have not tried it, so I wouldn't know how long they last in this system.
Thank you. Talking of scaling up, we have a question here for you, Chin. How much quantity could be produced using each of our systems?
Sorry, can you repeat the question?
Yeah, sure. So for the scaling up on each of our systems that you mentioned, could you just touch on the quantity that we can produce on the systems?
I cannot clearly hear your question due to maybe signal is not stable. Sorry.
No worries. I'll try again one more time.
Yeah.
Yeah. Sorry about this.
Could you talk about the scaling up capabilities of our systems?
Okay. Yes. So for scaling up the capabilities system, so because we use with hydrogel with production in space application, so we have, as I introduced, we have a tailored system. So thus we have multiple channels that integrate into one chip. We can running in parallel, and also we can running in multiple chip parallel together with the system. So the production rate would be increased up to 70 times compared to the single channel chip. So it could be run up to 30 mil per minute of the production rate, and for a month it could be generated up to a ton per month of the throughput with using the maximum the capability of the system, like 10 chips working together.
Mm-hmm. Okay, great. And then one last question for Anna, just before we finish up today's session. Could you talk about the viscosity of the polymeric solutions that you use to encapsulate the particles, and if you could potentially go to a higher viscosity than what you currently use?
Good question. I haven't measured the viscosity in liquid form of these. I've measured the viscosity in gel form, so I know a little bit about that. But viscosity is essentially your enemy when it comes to using systems like this. If your viscosity is too high, it's difficult for your pump to push through, and therefore you have more blockages, you have a slower encapsulation rate. It's just, there's a certain viscosity that you actually just can't get through this system. So that's why we use low melting point agar, because it's got a lower viscosity. And when I use alginate, I use the low viscosity alginate in order to get it through the system. at a faster rate. So I wouldn't recommend using highly viscous polymeric solutions in this microencapsulator system at all. I would go low as possible in order to set it and have a nice microparticle or microsphere.
Great, thank you. And that is just to time. I think I have gotten most of the questions, but if not, we will try and endeavour answering them offline with the relevant party. But thank you so much to both our talkers, Chin and Anna. I hope everyone's enjoyed their really engaging presentations. And thank you very much from Dolomite Microfluidics.
Thanks, guys. Thank you so much.
Thank you, everyone. Thank you. Sau cái sticker